This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello. Okay, it's 20 past. So let's get going. Are there any questions from previous week's material or anything that people want to raise before we get started? Okay, don't need to be shy. And you're welcome to ask things at the end, of course. Okay, so today's topic is text classification. So we saw classification last time in the guise of re-ranking of queries or query results, in that we were using machine learning model in order to decide which of the options that were retrieved should be displayed to the users in which order. Text classification is another instance where traditionally it's solved by machine learning models, and a lot of the tasks that you might sort of relate directly to language processing sort of fall into the banner of text classification. So this is, and so today what we'll talk about is the fundamentals of classification, and in particular the classification tasks. So various tasks that are useful within language processing that can be framed as this kind of classification scenario, where we're given an input and we have to predict a label. The input might be a document, it might be a sentence, or various other textual unit here. I'll talk about a few different algorithms for classification. Now, depending on how you've come into this class, you will either know a lot about this or at least a little. You will have seen many of these classifiers, so this should be a review for you. Notice that there is information in the reading that goes into a lot more detail about these various classifiers if they're not familiar to you. And I'd suggest you have a look at that if you need to. And then finally, I'll talk about evaluation, how we evaluate text classifiers, which hopefully should already be familiar to you to some extent. Okay. So classification, this is something you will have seen many times before. The idea is that we have a document here, and we're calling this D. We're going to try and learn a function that takes this document, or a description of this document, some inherent features of this document, to try and then predict an output class. So our output classes we're denoting with the value C, and potentially we might have two of them in some cases, the standard binary setting, or we might have several of them, in which case we denote it K. So this is not a continuous problem, it's not regression. It's usually not an ordinal problem, although they do sometimes arise. So there's no specific information in the order of class 1, class 2, class 3, class 4, but they might be very different things like politics, sport, and so forth, right? And so what we want to do is we want to learn a model that can take this input document, it can extract what are the useful bits of information from that document, and that's the feature extraction stage. And then it's going to weight these features to decide what the class is going to be and try and make a prediction. So we typically think of this as a two-stage process. One where you, as the person doing the modeling, you have an idea of what features are going to be useful, and you will then design them into your system. And then a machine learning, you give that as input to a machine learning black box. That's going to then learn from some data what the weights for each of these features are in order to predict the right labels. Okay. But before we go into actually how some of these classifiers work, I want to briefly look at various different text classification tasks. So there are many, many, many text classification tasks, and probably several hundreds if you were to sort of trawl back through the literature, maybe thousands. But here are a few sort of really common and illustrative examples of the range of different text classification. So I'll go through each of these at the bulleted points in some more detail, and I'll give you examples of each of these. And you may have heard of things like topic classification. You've got documents. You want to try and work out what the document's about. There's sentiment analysis, which is very popular within industry, which is where you're saying, is this document positive or negative towards a certain thing, for instance? Or is it just positive or negative? Is someone saying something that's effectively trying to say something nice or say something nasty? And various flavors of this, which is, particularly useful if you're a company and you're looking at mentions of your company, say on Twitter. You want to know what people think about you. Authorship attribution is another interesting one. So sort of getting more towards the forensic side. If we have a document, we don't know who authored it, can we associate that with a specific author automatically? And what are the telltale signs that allow us to do that? Related to things like native language identification. If all of you were to write a small story, for instance, then looking through the way in which you use language, we might have a decent chance of predicting what your first language was, say. Because there are certain things that come out in the way you write that can give away, particularly in terms of mistakes or in terms of various grammatical constructions that you might use more commonly than other people who come from other language backgrounds. And finally, I'll talk about, this is kind of a very new task, but this is automatic fact-checking. Idea of trying to work out whether or not a fact is correct or misleading or incorrect. Okay, and so common to this is the idea that we have some kind of text snippet. We're trying to make a categorical decision on the grounds of that text snippet. So it's a classification problem. Now, that text might be a document. It might just be a sentence, or it might be a tweet, it might be a small snippet from a document, for instance. So it varies as per the task. Okay. So topic classification is one of the most long-running tasks in language processing. So it's particularly useful, say, if you're in a library setting where you're trying to say for a text which of the categories should it be associated with. So in the library, you notice they have this Library of Congress and Dewey Decimal Number and all of these ways of organizing all of the text that they contain into an easily accessible collection. They want to put all the cookbooks together and so forth, so they need to be able to work out for this book, where does it fit in the hierarchy, where should you put it on the shelves and so on, so then it can be found more easily. So in library science, this is particularly important. This is the kind of metadata that you'll need alongside each text in order for it to be properly inserted into the collection. Now, this metadata could be manually assigned, but if it can be done automatically, then that's great. That saves a lot of effort. This is potentially also of use within information retrieval, where, say, you're interested in retrieving documents, but you're going to get you want to filter that down to a specific type of document. You're interested, say, in patents about evaporation of water or something, right? In which case you want to actually be able to say, well, I want to limit my search to just these category of documents, for instance. So if you have these categories already, then that's great, but if you don't have them, this is the kind of thing you'd like to automate. Okay, so the classes then are things like topic categories. So in the patent classification setting, you might have a list of 500 different categories, for instance. In the case of in the case of libraries, you're going to have this this hierarchical classification inventory. Sometimes they're flat, sometimes they're hierarchical. In our case, we've got examples like we might be dividing news or dividing health into all the different topics and so forth. And this is going to be specific to the problem domain that you're looking at. Now, the features that we're going to use to do this. So this is, each of these different tasks are going to differ in the kinds of features that have been shown to work well. So Sometimes you might have it might be fairly apparent from the task what features will work. Other times you might have to have established this through trial and error. Now, in the case of topic classification, usually our documents are fairly large. There might be books, there might be news articles, but they're going to have, potentially many hundreds or thousands of words. Consequently, looking at very fine-grained information to do with the word sequential order is not necessarily that useful in topic classification. Just knowing that the word exists is probably more important than knowing, say, the phrases or the syntactic structure or other sort of much more deep level of information. So consequently, people tend to use bag of words. They tend to do things like stop word removal. You might also do things like stemming and lemmatization, perhaps. It depends on the task. But you can be a little bit lossy in terms of how you represent the document in a way that's amenable for future processing. We might also use some bigrams and trigrams for important phrases. These might give us some extra information. Okay, but by and large, people will use bag of words. It would be the first approach to doing topic classification. So what bag of words means is that each document is represented as per in what we were looking at in IR in the last few weeks. We're saying a document is just represented by the counts of the words that occurred in that document. We don't care about the order. We just care that the word fish occurred 5 times and hunting 3 times and so forth. And that is going to be our representation. Okay, so there are examples of corpora in this space. So here's a few. There are many. So the Reuters news corpus has often been used as a test bed for text classification. There's a sample of this in the NLTK. It's a whole lot of news articles, and they have some topic assigned by the news agency as to which element of news they were relating to. There's things like PubMed abstracts. So PubMed is this online database of abstracts for medical work. They have many, many millions of entries, and it keeps growing all the time. And trying to predict, say, what element of health and medicine that these abstracts pertain to is obviously important in order to make this collection more useful. Another one is tweets with hashtags. So you could try and predict the hashtag of the tweet. You could try and predict various other things about the tweet that could be framed as classification. Some people will also look to predict the smiley versus grumpy face if they have an emoticon, for instance. Yes? Well, so if they're informative n-grams, you might not want to use all of the n-grams. I just leant on this and it started going up. Surprise. Yes, you might not want to use large n-grams without knowing that they're going to be useful. So there are going to be some words that are not going to be informative on their own, but they're going to be useful in context. So you might have words that are, if you're interested in things about, agriculture and aquaculture, if you see the word fish, it might not be that useful in that it's a generic word. It's going to be used quite widely. But when you see, fish stocks or fishing resources or various other bigrams including this, maybe then they've got this meaning that sort of you wouldn't attribute to each word on its own. So a lot of the work in this space, they might start out with bag of words, but then they might incrementally build up bigrams based around them being informative. So there's a whole cottage industry in trying to do feature induction in this space, which is usually done as this incremental process. You start with something simple, and then you say, here are a few candidates. Let's check to see whether or not they have high mutual information, say, with our target label, and we'll incrementally add them. And we're just going to keep doing this round after round until we build a figure-feature representation. So that, if you rewound 10 years, that would have been state of the art. Now everyone does things with neural models. If you have a very big data set, then these neural models can learn these things automatically. So people tend to use convolutional nets, which when you apply them over language, they can look at, say, a single word, or they can look at several words. So if you had a convolution of width 3, that means you're going to have features that look at triples of words, 3 words as an n-gram, and then that slides over your input representation to form a representation. And so the idea there is that it can automatically learn a lot of these bigrams and trigrams and so on, just by having access to all of them, and then learning which ones are most useful for classification. Are there any other questions? We'll talk a little bit more about neural models later on in a later lecture. I don't think I actually planning to ever talk about convolutions though, but there's actually some good reading in the textbook, the Eisenstein textbook, about this kind of thing in some of their chapters. Okay, so a topic classification example. So we've got this text, I'm about to show it to you. We've got, say, we've simplified it to a binary decision. We've got two classes. Is it about acquisitions or is it about earnings? So these are both financial topics, but we're going to have to figure out which one. I'll let you read it. Unfortunately, it's very boring. It's about finance. A lot of the text corpora are. Does anyone think it's about acquisitions? You can raise your hand. Got a few tentative hands. And what about earnings? There was one half hand that went back down again. So I think people, the ensemble or the aggregate agrees acquisitions, which is correct. So that's great. So this has been manually tagged by Reuters as acquisitions. And this is the exact kind of thing and the way we have several thousands or hundreds of thousands of these, well, there might be tens of thousands in this corpus of examples like this, and then the idea is to learn a classifier. And so what the classifier is going to do, it's going to concentrate on, it's going to try and learn, say, if it's trying to learn a bag of words representation, it's going to see there are words like merger. There's going to be another one, merger. So merger's got a high count here. It's got subsidiary, merger again. Receive shares might be a good bigram or trigram. And these are all going to be evidence that there's some kind of acquisition going on, right? So were we to train this over a large enough corpus, it should learn that some things are not very informative, like corporation and numbers. They're going to be relevant to earnings as well. Various stop words, like, well, in this context, stock might be a stop word because it's not particularly informative. But all of the things like of and that and so on are not going to be particularly important at all in this case. It's going to be largely just down to what are the nouns and what are the verbs, maybe. And yeah, it's going to be looking for particular ones. Okay, so sentiment analysis is very closely related. It's another instance of text classification. People use it a lot of the time to try and work out what opinions people have, particularly towards a stock or a product. So were you to say, search for Google Pixel 3 or whatever they're up to now, maybe it's 2, sure. Anyway, and then look to see for their corpus of tweets, if you're trying to then say, or blog posts, say on, trying to see what people are saying positive versus negative things about this. There are more fine-grained examples of this where you're saying people are talking about this product, they might be saying a positive thing and a negative thing in one passage, right? They might be saying the camera is good, but it's very slippery to hold, for instance. So they've said two things. They've referenced two different aspects, and a lot of the more recent work in sentiment analysis is looking at aspect-based sentiment. So trying to detect what aspect is being referenced, and then detecting the sentiment relative to that aspect. But in this case, I'm just talking largely about a small snippet of text, and is the polarity happy or sad, positive or negative, or perhaps neutral. And a lot of the work here has started on things like movie review databases. So things like IMDb, Rotten Tomatoes, all these kind of things. You can get a lot of text. You can get critic text. You can get individual text. And most of the time, people give it a star rating. So it's very easy to use that to create a corpus for testing out and developing these kind of classifiers. So there's a polarity movie review set in NLTK. There's various things in Twitter about people's polarity towards politicians, towards products and various things. The Semival competition runs every year, and they've always got various tasks that are some kind of sentiment-related polarity tasks in this space. Okay, so in terms of features, what are we going to use? Well, by and large, they're usually often very short. So if we just took a bag of words approach, we might lose some nuances. We might have to go a bit deeper. We might use n-grams. We might actually go to some lengths to normalize the text to deal with misspellings and all these other things, like I talked about in the first lecture. just so we get a more general representation. And if we're dealing with tweets, we have to deal with @ tags and hashtags and all these other difficulties, which we need to process carefully as well. But in terms of the features, we're going to have a feature for various n-grams, and we also often have polarity lexicons. This is where people go to great lengths to list a whole lot of words and saying this is a happy word, this is a sad word, and so on and so forth. There are various word lists counting in the many thousands of words where people have said these are loaded words with regards to sentiment. And some of the early work was just doing counting, right? Saying that here's my happy words, here are my sad words. How many happy words versus how many sad words? If one's more than the other, then this is a happy tweet. Otherwise, it's a sad tweet. It's a very simple approach. It's not really very effective, and it doesn't really get to the nuance of what is being said. So more recent work tries to do that in a more interesting and sort of linguistically coherent way. Okay, so here's an example. This is from Semival. You can read it. Okay, I think that's pretty obvious what it is. It's negative. And so, yeah, this is particularly useful in this case for Microsoft to be able to understand whether or not people are happy with their system, happy with their updates, and so forth. Okay, so another task, the next task is authorship attribution. So this one's kind of pretty cool. You might be interested in plagiarism to work out, did this German MP really write their thesis, or did they get someone else to write it for them, for instance? Of course, lots of other people plagiarize as well. In forensic linguistics, if you have a written sample of text from someone, can you associate with that with an individual with any confidence? And so often people in the research world tend to use things like Project Gutenberg corpus. So Gutenberg was the first developer of the printing press, I believe. And there's this project that's been named after Gutenberg where they take a lot of out-of-copyright works and they make them available for free. So a lot of classic books from sort of 50, 60 years old and older are available for free online, many hundreds of texts. And so we can use these, get snippets of text out of these, and we can frame it as an authorship attribution task. So if we're trying to work out, for instance, was this written by Shakespeare, or was it written by another poet, for instance? Or was it written by Jane Austen, and so forth, right? So in terms of features, now this one's kind of interesting. We're not looking so much at the text because that's going to be very specific to the book itself, and maybe not so specific to the author. So, for instance, if you know the names of the characters in a book, okay, it's fairly easy to work out that it came from that book. But if we're pretending this book hasn't existed, this is a fresh piece of work that's just been discovered by an author, the names of the authors are not, the names of the characters in the book are not going to be so useful. And the things that they're doing might not be so useful, maybe at a high level, but when we're trying to get down to fine-grained distinctions between two authors, it's not so easy. Yes? Yeah, I'm not sure, actually. I think it might be more difficult in that case. So often people do frame a variant on this, trying to work out how advanced people are in their learning. So people who work in educational testing service and so on are looking exactly at these kind of things, right? Automated grading of essays and so forth, and learning tools and so on in this space. I'm not sure how that dovetails in with authorship attribution. That's an interesting question. I don't know if there are corpora available for that kind of thing, because it's fairly hard to get corpora written by individuals who are not very good necessarily, and for which you know that. So yes, you can get Twitter, you can get a mixture of things that are very well written and very poorly written, but it's kind of hard to characterize where they fit in the spectrum. There's a whole lot of privacy guidelines around this as well. But yeah, I do know that people do it as learning tools and so on, and trying to integrate that into learning pipelines. But yeah, okay, so what we're looking at here often is frequencies of function words, which is kind of interesting, right? So if you see that people have telltale signatures, like in terms of how often they use of versus for, or above and below, and so forth, right? So if you look at prepositions in particular, you can see that there's actually quite a lot of biases between different authors. That it's a sort of stand-in for the kind of grammatical structures that they use and their biases between one versus the other. And you can get some of this quite easily by looking at the distribution over function words. You can also look at character engrams to get a clue for the kind of words and the kind of lemata and so on that they use, as well as the kind of tense that they use more regularly. Also things that are more higher level, like discourse structure. So the use of more complex discourses, particularly in novels, you're going to see this kind of structure come out. Do people have, say, a whole lot of dialogue? Do they have sentences with a whole lot of structure where one sentence is building on the other? You see lots of therefores and other connectives that connect the passages together. And these can often get to what the sort of fundamental style is being used by the individual. I'll give you an example. Now, some of you will either know or you won't, but if you look at this, you can see firstly that the language is not very much in the sort of very modern style. It's definitely from the past. And this is actually an example of Jane Austen's writing. It's a snippet from one of her novels. And a lot of the times, if we can learn to generalize this so that we don't get too bogged down in the domain of the document, like what topics it about, where is it based, and so on, can we actually learn the underlying style? Then that will generalize better to other types of writing by the individual. There's an interesting body of work in a related topic where they were looking at Agatha Christie as she was. So what disease did she have? Did she have multiple sclerosis or Parkinson's? I can't remember. She had a degenerative disease, and you could actually tell in her writing, because she was continuing to publish at quite a high rate, you can actually detect where the disease was kicking in. And her writing, actually, there were signatures in terms of how her writing suffered as she, I think it's Alzheimer's, sorry, as she degraded. Okay, native language identification, this is another one. Trying to detect someone's first language. This one is actually surprisingly accurate. And in this case, we're going to look at things like the words people use, because word choice is key, so things like word engrams. Syntactic patterns to see what kind of structures they use. We might also use things about the phonology, that the patterns are going to be a little bit different. So there are some corpora about people writing essays and so on, coming from different language backgrounds, trying to learn English. So, people also use some multilingual data, like the European parliamentary texts, for instance. They're translated into lots of different languages. You can try and identify what language was the original language that this was translated from, which is a related task. Okay. So this one's a bit harder. Does anyone have any guesses on what the native language for this is? So there's a bit of whoops, you can't see it. Sorry, you should have told me. Now I look around. I was wondering why you're staring so blankly. So towards the end, you see there are a few grammatical mistakes. I found it puzzled to manage an event without generating a free rider. So does anyone have a guess? I should have got you to do a clicker thing so that people could do it anonymously, because it might seem a little bit dodgy. Okay, so they're Japanese, this person. And there are some clues in terms of how they did, I'm not sure exactly what the clues are, because this is not my research area, but I believe that the way in which, mistaking things for plurality, getting some verb, noun agreements wrong, saying things that are just sort of slightly stilted, these kind of information can give you some signal about who wrote this. Okay, let me move on to the last topic, which is automatic fact-checking. So in this case, this is kind of a really hot new topic that's come about in the last 2 or 3 years. The idea here is that you have, You have a lot of social media, you have a lot of journalism that comes about through Facebook and so on, where some of the claims are slightly dicey and you can't believe all the things you read. Can we automatically go about trying to detect whether or not something is true or false? Now, in this case, the features might be just looking at the claim itself, or the features might be looking at some evidence that is related to the claim. So were we to search the web and find other information on this topic, can we judge whether or not the claim is true or false? And the features here are largely question mark, because it's a very new task. Yes, you can try and classify it just from reading the claim, saying, does it feel like it should be true or false? Does it look like it's misleading? In which case, you can use features common to some of the things we've shown before. You might be trying to use metadata to say, what is the context in which this was uttered? Who said it, when, to whom? But yeah, a lot of the time you might actually be searching for other supporting information, and that might be the strong clue as to whether or not it's true or false. And there are various new corpora in this space. Okay, so here's an example. Austin is burdened by the fastest growing tax increases of any major city in the nation, assuming in the US. The answer happens to be false. How you would know this without having any background information is very complex. The way to actually establish whether or not this is true or false would need some kind of retrieval engine. So for instance, were you to search for tax in the US, were you to search for Austin, various other things, find some good documents, find some instances that are on topic, then you might be able to do this, which makes it a little bit more complicated than the other scenarios, in that you're not just having one snippet of text, but you're potentially having several. Okay, are there any questions? Yep.
How fast checking is a classification problem as opposed to being just an information retrieval problem?
Well, so if you want to, so if you have some, so step one might be an information retrieval problem, and then step two, based on having retrieved some information, can you classify it as true or false? So with this example, were we to then go to Wikipedia and find the 3 or 4 pages that were related, based on those documents and this claim, can we then automate the judgment of true versus false?
So that the output that
Becomes the input. Exactly. It becomes part of your feature representation. Yes. So instead of just having n-grams over the claim, maybe you also have contextual n-grams over where you see that claim referenced in a larger document. So this is where the creativity comes in, how you actually do this. And this is a lot more complicated. It's sort of an illustration of the more complicated instances of text classification that you see in practice. Okay, so how do we do this? This is sort of the key steps of training, building a text classifier. So we identify our task, collect our corpus, carry out the annotation. Now that steps 1 through 3, most of the time what you're going to find perhaps is that if you're doing a task that's of interest to others, there are corpora out there, they've already been framed as a task, the classification label has been established, the data has been annotated. And you would often start off at step 4. So step 4 is saying, okay, now for each of our instances, say they're sentences, how do we represent them as features? Do we have a bag of words representation? Do we go with something else? Once we have this idea, then we can represent them as a vector. And is everyone sort of familiar on how we would go about representing them as a vector? Because I don't really go through it in a lot of detail, but I can just give a little, I'll give a little detour anyway at this point, if I can turn this on. That's right. So I'm just going to show you some text from the textbook. So I changed the reading. I added some extra reading, an alternative reading, into the Eisenstein textbook here. So I'll go through this in a sec. I think the coverage of text classification is a little bit better in this than the previous reading that I had written there. You're welcome to read either. They both cover the same space. But I'm showing you an example here from the Eisenstein textbook. So the idea is, imagine we have a bag of words feature set, right? So we're trying to predict, we want to predict something from a bag of words representation of our document. And what we're going to do is say, their instance here is saying we have the word whale versus we have this word molybdenum, I don't know how you even pronounce that, which are going to hopefully be formative, right? So if we're trying to classify a document as being related to fiction versus something else, in this case, chemistry, for instance, we would expect the presence of the word whale to be more closely associated with fiction and the presence of this other word to be more associated with chemistry. And so the way we frame this is effectively we define this function f, which is basically saying we have our document, our text here, which might be our sentence, say, or our document. We have a candidate label here, which could be fiction or it could be chemistry, for instance. And we have this function. So this function takes the input of the sentence and the label and an index j. So this is an index here. And the idea is all it does is it basically does this test, right? Saying that if the label is fiction, in this case, it's going to return the presence or absence of the word whale. So if this is a binary feature representation, x sub whale will just be 1 if the word whale exists in x and 0 otherwise. If it's a term frequency representation, then it will be the count of the number of times the word whale appears in the document x. So effectively, feature j is saying, does whale exist and is the label fiction? Now, we're going to have lots of features like this. So that's why it's f sub j. We're going to potentially have 100,000 features like this. We're going to have one for each word in our vocabulary, and we're going to have one for each target label. So if we have a 50,000 word vocabulary and 2 labels, we're going to have 100,000 of these such features. Attached to each of these features, we're going to also have a weight here, right? So this is most machine learning models can be framed in this way. So for instance, logistic regression, that we'll see later, is an example. Perceptron learning, another example, and so on. What they basically say is we're going to have a feature representation of our input representation and a candidate label. We're going to have a whole lot of features. This would be the 100,000 features J here. And we're going to basically say the score for a document, which we're representing as this symbol phi, is just going to be summing out each of the features and multiplying them through by our weight. So we're going to have these guys, theta are our weights. We're going to have, in this instance, 100,000 weights. These are the learned parameters of our model. When we train it on data, we try and learn these weights theta so that it makes the correct predictions. So that the score for document X is highest for the correct Y. So if that document is actually on fiction, then the score, the phi function for X and fiction is a lot higher than the score function for X and any of the other topic labels, in this case, chemistry. So this is a standard way we do it. And so when I say bag of words representation, what I mean is that each of the features look like this. They're basically just saying, does a word exist, or what is the count of the word, and what is the label? And what we end up doing, let me show you here, when we have several different targets, something like this. So we have our original text coming in on the left. We represent it as a bag of words vector. So this is our entire vocabulary here. You can see it's in sorted order. And we have a representation of the count of each of the time the words occurs. So up to here is our vocabulary. And we have a special value that we always set to 1 for everything. I'll explain that in a sec. So this is exactly what we had in the IR context. Notice here that we haven't got rid of stop words. It depends on the context as to whether or not we do. Then what we'll do is we'll basically say that we have the bag of words. Each of those elements in the bag of words plus a label gives rise to a feature. this word plus label news gives rise to a feature here. This word plus label gossip gives rise to a feature here, and so on and so forth, right, with each of these. So in our case before, I was saying we had a bag of words that was, say, 50,000, and we had 2 labels. Now we have 4 labels, so we have 200,000 features. The first 50K are 0 because we're testing it against news. The last 100K are 0 because we're testing it against label news here. So if we find a representation of this, that it's effectively just saying what is the bag of words and the label equals news here. So this then forms an input representation. We can then throw this into many black box classifiers to learn how to take this, how to weight it by a vector of size 200K, in order to then get a scoring function to say how well does this document represent fiction, how well does it represent news, and so forth. Okay, and that's what our learning is going to be doing. Does that make sense to people? Hopefully people have seen this in knowledge technology and so on, and this should not be particularly unfamiliar. But stop me if it is. Yep. Sure. So some machine learning algorithms stop you from, well, limit the ability to have certain features. So naive Bayes, for instance, makes an assumption that all of your features are independent given the class. So that means that, well, it's a pretty bad idea in general, but it often works. But were you to have unigrams and bigram features together, assuming that a unigram is independent from the bigram is completely untrue, because often they will actually contain the same word. If the bigram is fishing rights, then the unigram fishing and the unigram rights are sort of implicit in the bigram, right? So they're perfectly correlated in that case. Now, other models, such as neural models, effectively do away with a lot of the feature representation. They tend to just say, give us the input as a sequence and we'll process it and automatically extract these things. So you don't need to do a lot of these pre-processing steps and feature representation ahead of time in that case. Sometimes you still choose to, but oftentimes you just wouldn't, because it's a lot simpler, and these models actually tend to be quite good. So yes, it does depend on the model. Some learning setups won't work with 10 million features, which is not that weird a sized feature vector to end up working with a lot of the time on one of these larger data sets, where you have hundreds of thousands of vocabulary items and very, very many classes, for instance. Like pattern classification, you might be working in that space. So scalability might be another concern. But yeah. Okay, sorry, what were we up to? Select 4. Choose a machine learning algorithm. There's a whole lot of algorithms that work quite well. And I'll briefly just name drop a few of them. And then we want to tune them to our data set, right? So if we're using logistic regression, it's got a smoothing parameter, say. How do we set that smoothing parameter? Well, that's going to be something that we're going to have to decide on our development data. There might be other hyperparameters, like hyperparameters to do with how we process the data, like did we stem, did we stop, did we trim our vocabulary, trimming out rare words, all these kind of things. They might be variables that we tune on our development data as well. So we don't do this on our test data, because our test data is supposed to tell us how well we'll do in general if we see fresh information, fresh text that we haven't seen before. So we do this on development data, and then once we've established all of the variables, the setting for our algorithm, we have our core method, then we can test it on some fresh data that we haven't seen before. Okay, which is that step 9 here. Okay, so choosing a classification algorithm. So sort of gets to the question before. If we choose a model, an algorithm, and a method that is very, very richly parameterized, then we might end up learning a model that can represent a lot of noise in the corpus, but doesn't actually generalize too well. Now, if we have a very, very large training corpus of millions of examples, then we can make do with a very richly parameterized model, and they tend to do very well. And a lot of the deep learning models these days have hundreds of millions of parameters, some of the larger ones. In fact, they might even be into the billions, some of the largest ones. But they're trained on, say, the entire web, some of these, or maybe not quite that large, but yeah, hundreds of gigabytes, perhaps into the terabytes, some of these larger training sets for these models. So it's a big, well, in that case, raises a whole lot of engineering efforts and so on about how you do that. But most of the time, if you have a tiny data set, you're trying to classify, I don't know, Jane Austen versus Emily Bronte, then you'd have a tiny data set. You'd want to choose a model that didn't have too much capacity so that you could be sure that it would generalize well. And this is relating to the bias variance trade-off, which you may have heard from your previous studies. So there are underlying assumptions behind some of the models in terms of what they're doing, how they frame the problem, the constraints they place on your features. There are also different complexity and different speed. And now, I'm not going to say too much about this because I want to cut to the evaluation, but I'll just mention some of the models that you might consider. Naive Bayes is one. I won't go through the details of it, but it's a probabilistic model that's saying, given a feature representation, what's the likelihood of the different classes? And that's framed through using this Bayesian inversion. It's very fast. It's not that great, but it's a good first attempt at a lot of these problems. And it tends not to get too widely used these days. For standard text classification, it actually does pretty well, by and large. Sorry, I should note that there is one caveat here where you are using this for text classification. If you have very rare words in your corpus, you might say that they have zero probability of co-occurring with a given class. Zeros can be problematic when we're doing mathematics. If we multiply through a whole lot of things, including one of them as a zero, the whole evaluation is zero. It's uninformative. So what we tend to do is smooth these by saying 0 becomes a tiny epsilon that's non-zero, and it means that we can still evaluate this mathematically without getting zeros or not numbers or various other things floating through. Typically, when we evaluate this, because we're saying we have m possible features here, and I said m could be 200,000, say, we don't want to multiply together 200,000 numbers that are very small. We would add together their logarithms instead. And that way we don't have problems with underflow or overflow, or underflow in this case, where the numbers just become zero. Okay, so logistic regression is another one. I'm assuming that you've seen this before. It's a classifier. It's framed as this multiplication of our weight times our feature function. The thetas from before are the w's here. So often they're referred to as theta or w, depending on the context. And the idea is that it pushes this scoring function through this sigmoidal shaped function. And the idea is that values that are very high magnitude positive end up being associated with the probability of the class being close to 1. Values of this that are very negative end up being thrown through the sigmoid function and mapping towards something that has a probability close to 0. So we can treat the output of this score function sent through the sigmoid as a probability of the class label. And that's the idea behind logistic regression. You can use it for binary classification, which is where you have this pretty sigmoid. You can use it for multi-class classification as well, based on what's called a softmax function, which is a generalization of the sigmoid function to multiple variables. Okay, so this is a nice classifier. This, in fact, is probably the best off-the-shelf classifier that you could use in this setting. It can deal with any types of features. The cons are that it can be a little bit slow to train. However, if you've got a graphics processing unit like an NVIDIA card in your machine, it's pretty fast because that ends up being parallelized. It just does have this iterative training loop. It basically does a gradient-based optimization to find the parameters that best fit your training data. So it has a regularization parameter. It can be a nuisance to fit, but you have to. This is something that you have to tune for each problem to stop the model from overfitting. Okay, support vector machines are another one. I'm not going to dwell on them. by and large, they look a little bit like logistic regression, except instead of giving a probability, they give a weight, a score for how much this example looks like a positive versus a negative class. K-nearest neighbor is another one. This is actually surprisingly effective for document classification. So the idea is that if you have a point which represents your document, you look for other documents in your training corpus that were somewhere near your test document. And if you, in this case, we've drawn a circle around which are the 5 nearest points to this grey dot. And we can see that 3 of them are blue, so the grey dot is more likely to be blue as a consequence. So this requires us to, A, be able to search through our training set to find similar instances, which means that in the terms of bag of words representation, share as many similar words as possible. Effectively, that is just a retrieval problem, right? You are using the document as a query against a corpus as a set of documents, sorry. And then you're going to select the top K and you're going to average their labels, work out which is the most common. You need a definition of nearest. It could just be looking at the cosine within TF-IDF space, say, which is exactly the IR scenario. It could be something like the Euclidean distance. So the pros is this is simple, it's effective, it works really well, especially when you have a large data set. The cons are that you have to do this retrieval process to try and find the nearest items. It can be a bit slow. Now, if you have optimized indices and so on, and you choose your definition of distance in such a way that it can be optimized easily, cosine, for instance, then it's not such a problem. Yep. Sure. Yes, so if you see a document that's very different from any of your training documents, then you're in trouble in that lots of documents will be equidistant. The thing is, with text, you're likely to see that some words are a lot more common than others, and along those dimensions, you'll see that the document is quite similar. So it's sort of corpus dependent. I guess the point is that even though the dimensionality is very high, several hundreds of thousands, the set of points where documents actually lie is actually a lot smaller. So this is the so-called manifold in which the data lies is actually a lot smaller than the, what do they call it, the implicit versus the explicit dimensionality of data. This is getting into quite complicated questions of statistical learning. But in practice, what you find is that although k-nearest neighbor shouldn't work, it actually works really well. So yeah, as you increase the dimensionality, you have to be careful, because if you increase the dimensionality too much, yes, you get this problem. But if you're working with things like bag of words representations, you tend not to have the problem. It tends to work quite well. If you do things like IDF weighting as well, then the dimensions for which you have the for which count most towards the cosine are the ones that are likely to be most informative. If those are words that have only been seen once, yes, you're going to have a problem. But if there are words, if you have many documents that contain those high IDF terms, then you're going to get a bit of signal and you're going to be able to compute. Okay, another one is decision tree, but I'm going to skip to the end because we're to the evaluation set, because I unfortunately are running out of time. If you stick with me another couple of minutes. So the question is how we evaluate these things. So we have our model. It's going to make predictions. If our data set has certain classes, class A and B, and our model predicts class A correctly 79 times, incorrectly 13 times, and for class B it predicts incorrectly the class B's is A 8 times, and class B is 10, then we can quite simply work out accuracy just by saying these two on the diagonal are both the correct instances, and these two off diagonal are the incorrect, and we can add up correct divided by total, so correct plus incorrect, and we can work out its accuracy. That should all be fairly familiar to you. In this case, there's a very big class skew. A was much more common than B, so just predicting A, you would have been right a lot more of the time. Have I got the maths here right? Yeah, so you would have basically got it correct for 79 instances, and I think if that's right, you'd end up with a slightly higher accuracy. So in this case, accuracy isn't a particularly good measure. I'm not sure if that makes sense actually when I look at that, but I'll review it later in the interest of time. So what we tend to use is precision and recall, as you will have seen before, and I'll just leave. And generally, we go to an F1, just like, the use of precision is just like what we're talking about in information retrieval. But in terms of F1 scores and so forth, here, there's one point that I'd